Section 9.1, separable equations. In this session, I will introduce the differential equations. First of all, let's check what differential equation is. Differential equation, of course, play a fundamental role in engineering and also in different fields, because many physical phenomena are best formulated mathematically in terms of the rate of change. Using different words, I can say we can observe how things are changing, we can measure the rate of change. However, we will not have the function, like original function. We can't really define right away the original function. And then if we will derive the model, which includes that rate of change, an unknown function, then this indicates that we simply created a differential equation. Okay, so in one more time, differential equation is the equation that includes derivative, rate of change, of course, and unknown function. And the point is to solve this equation for the unknown function. That's always the point, to find the solution. And not always is an easy process. Most of the physical phenomena are quite complicated, and we have different ways to approach differential equations. One of the classification of the differential equation is if the equation includes only one independent variable, we will call this equation ordinary differential equation, ODEs. If the equation includes more than one independent variables, then this equation is called partial differential equations. And of course, talk really deeply about ODEs or PDEs, we will need another math class. I believe it's math 250 to 51. Probably most of you will take this class. Okay, but in this two sections of chapter 9, we will mainly focus on ODE, the ordinary differential equation, which includes only one independent variable. And also, another classification of differential equation includes the order. The order of differential equation is the largest derivative present in differential equation. Because we may know the first rate of change, the rate of change, let's say, of the distance with respect to time. Of course, it's the velocity, speed. We may have the rate of change of the velocity with respect to time. That's the second derivative. But the largest derivative present in the equation will represent the order. If it's just the first derivative, the order, we can say, is the first order differential equation. And if it's only one independent variable, we will say ordinary differential equation. And that's what we will look. As mentioned, solving differential equations is not an easy process, and not always we will be able to solve these equations explicitly. Before we start, let's look at this equation. Y prime equals to y. Of course, for some of the equations, we do have a nice explicit way to get the solution. But even looking at this model, this equation, you will probably tell me which function satisfies this equation. We may add some constant and some different things, but you can definitely tell me that the exponential function e to the x, it's definitely one of the solutions. Okay? Maybe we have different, maybe we can add a couple of constant, but definitely e to the x is the solution of this equation, because derivative of e to the x is also e to the x. And I can say they are both equal. Yeah. Let's look at something different. Let's say second order, which of course we will not focus, but just for now. Second derivative equals to the negative y. The second, like the the rate of change of the rate of change, the second derivative, is equal to the negative and function itself. And you can probably also think for a while and you will tell me, oh, some of the trigonometric functions, I believe they will work. Maybe cosine, let's say t, we can make it independent variable t, cosine of t. And let's actually verify. First derivative is negative sine of t, and the second derivative is negative cosine of t. Then if I will put second derivative is negative cosine of t equals to negative y, and y was cosine of t. Yes, this function is the solution of this. It's just one of the solutions, because we may play with some coefficient or some additional, but yes, we did guess and verify that this is the solution. I can box the solution. This is the unknown function, which actually is known. Okay? So that's also one of the way, like to, if we have a model, differential equation, for instance, let's say 4y double prime equals to negative 25y. This equation looks a little bit like the second one. Okay, but we have some coefficients 4 and 20, negative 25. I mean 25 because negative was part of this function. Then we may think, oh, we need to find out what function will satisfy this equation. And again, this is the second order. We will definitely not focus on solving algebraically. But what we can do, I can suggest a function. For instance, I can say, I'm thinking that function cosine of kt, k is just coefficient, is the solution. But we have to verify for what values of k this function actually will satisfy this equation. We are confident that cosine function works. But what values, what parameter k will have to be in order to satisfy these coefficients 4 and 25? Okay, what we will do, we will basically find the first derivative. Derivative of cosine of kt is negative sine of kt times k. Follow the chain rule. And the second derivative of negative k sine k of t, derivative of sine is cosine of the same angle, kt, and times another k, it will be k squared. Okay, now our equation is 4 times second derivative, negative 25 times the function. 4 times second derivative is negative k squared cosine of kt minus 25 equals to negative 25 times function itself, cosine of kt. Okay, now let's solve this equation for k. I will add 25 cosine of kt to both sides of the equation. And then we will have negative 4k squared cosine of kt equals to 0. Let's factor out cosine of kt. Then we will have 25 minus 4k squared. And zero product property will tell me cosine of kt. If it's 0, the whole equation is 0. Or 25 minus 4k squared equals to 0. Then solving this for k will give us 25 over 4. Taking the square root, we have positive 5 over 2. And if k is positive or negative 5 over 2, we will have this function cosine of kt will satisfy this differential equation. Okay, that's the if k equals to positive or if k is negative 5 over 2. Perfect, that's the solution. Of course, we will not really talk about this because if cosine is 0, then everything at 0 doesn't make sense. We will not talk about these solutions. Okay, so we can see that's one of the way, and we may occasionally see these equations and a potential function that's satisfying this equation, and we have to verify for what parameters, for what values of the parameters k, this equation will work. And we did it. Okay, now let's look, let's solve the equations that we can actually, we are lucky because in this section we can focus actually on the equation that we can solve them explicitly. Yeah, as I mentioned, not all of them, but some of them we can solve nicely using basically some calculus tools and get the equation, get the solution to know the unknown function. Unfortunately, this is not always possible because the physical phenomena, like the general real world problems, are a little bit complicated. I can just quickly mention we do have some approximations method, if we like some numerical and some graphical. If we are not able to solve algebraically, we can use Euler's method for the numerical values. Okay? It's kind of like tangent line approximation. I hope we remember a little bit from calculus 1. Or we may use direction fields. This is more like geometric approach. Direction fields, or sometimes it is called slope fields. Since differential equations includes the derivative. Derivative is basically slope of the tangent line or slope of the curve at the given point. We may work with those little line segments and approximate the solution, but we will most likely not talk here about these methods, but I would like tell you that these methods exist. Okay, let's look at these differential equations that are easy to solve. This will be separable equation. Separable equation is a first order differential equation in which the expression for dy dx can be factored as a function of x times a function of y. In other words, it can be written in the form dy dx is equal to a product of function which depends on x times function which depends on y. And we will separate everything, okay? We will separate the y and the x variables. Of course, x is independent, that's the only independent, and that's ODE. And y is dependent variable, but we can split them. dy dx we will treat as a differential, and we will also split. We may have a little bit different form. We may have like a quotient of both of these functions. And this will be also different, separable differential equation. Okay, now let's look how we can do this process. This is one of the form. Okay? Let's see how we can make the separation of the variables and then take care independently for y and for x. Okay, dy dx equals to f of x times g of y. Of course, different notation will tell me this, y prime. That's just in case if you will see y prime, you can rewrite this as a dy dx, just the Leibniz notation. And now what I will do, let's see. I will divide both sides by g of y, the function which depends on y, and keep dy, and move dx, like kind of like multiply both sides by dx, and f of x will stay on the right-hand side. Okay, and we can see all of the y's on one side, all of the x's on the other side. And now is just the moment that we can, since we have this dy dx, we will integrate. And hopefully both of the integrals will be relatively easy to process. Or we may have that form, dy dx and just the quotient of function g and h. G depends on x, h depends on y. And I can kind of say cross-multiplying. I will multiply both sides by h of y, and then I will move the x on the other side. And the same thing, now we good with the independent and dependent variable, and we can process here. This will be the couple of first steps for the separable differential equation. And yes, all of the y's go on one side, all of the x's go on the other side, and we can integrate respectively. Yeah. And then at the end, of course, we will solve. We will solve for the unknown function y. If sometimes equation will give us like the form that we will be not able to solve for y, we can leave it in the implicit way. Okay. Just a couple of notes. An expression for a family of solution to differential equations it's called general solution, just the general solution, because we notice integration is involved. And always when we integrate, the answer is the family of the function. It's not just one particular function. It's a family of the function because couple of functions can have the same derivative, the same rate of change. That's the reason. We know the calculus part. However, when we will have given initial condition, like let's say we would like to have the initial value when time is, for instance, 0, we want 10 like degrees, or we want 10 like amount of some population. Then we will call that these are the initial condition. We may substitute these values, okay, and solve for the constant c. And then if we will have the constant c, we will, actually having this initial condition and having the constant c respectively, we will get one particular solution. It will be not a general solution, will be one particular solution. And this we will call that this is initial value problem. Initial value problem, it's one unique solution. Okay, and now I have just three examples. The first two are the separable differential equation. We can nicely see, we see the product of function y and function x. For the second one, we might think that it's not easy, but when we factor out x, we will have 1 plus y. That's also separable. Actually, I can even write, we will divide both sides by 1 plus y and keep dy. We will keep x and move dx. And now we can integrate. Okay, but we will do this later. And the same for this one. I can divide by y, keep dy, keep sine of x on the right-hand side and move the x. And we will integrate both sides. Okay, that's actually nice equations. However, number 3, we see x plus y. We will be not able, because of this, we will be not able to make this separation of the variables. We will always have x plus y. I can't factor out x or y because we will always end up with 2 factors including x or 2 factors including y. Okay, that means this equation definitely needs different attention. Okay, let's solve first question. Consider the equation, differential equation, dy dx equals to 1 minus 6e to the power of 2x. Find the solution, the general solution, and then find this particular solution, initial value problem. If x is 0, the value is 5. Okay, let's start. Dy dx. actually this one, we don't even have to do anything because we may notice basically just the x function is given. Y function is not, the implicit way, of course, of the y function is not present. Okay? That means I will keep dy on this side and I will move dx. And now we nicely see that is the separation happens and we can differentiate. Okay, we can integrate, of course, we can integrate. Integral of 1 dy, it will be y plus the constant c. Let's just put c1. Integral of 1 dx is x, copy the constant. Integral of e to the 2x is e to the 2x over 2, and plus another constant. And okay, let's solve for y, x minus 3 e to the 2x, and we will have constant and constant. And what is important, we're not really involving constants in any arithmetic. If we have constant times another constant, constant minus another constant, or even better, like multiplying constant times 2 times 3 times negative, it will be always a constant, just like another constant. That means let's just keep it this together. What we will do later, we will not even write this constant on the left-hand side. We will basically add one constant, common constant, on the right-hand side. Okay, that means the solution for this equation is x minus 3 e to the 2x. I am making some weird typos. And plus that green constant. Okay, this is our function. But this is the family of the function, because we can see we can move up and down, c units up, c units down, depends what c is, the constant c. But if we would like one particular curve, we have a condition. We would like to see what is the constant c if x, substituting for x0, the value is 5. Okay, the equation is x, which is 0, minus 3, e to the power of 2 times 0 equals to 5. This is, of course, e to the power of 0. E to the power of 0 is 1. Oh, I lost a constant c. This is 1. And negative 3, we can add negative 3 to both sides. Constant c is 8. And then our equation, y of x, I can be more specific, indicating independent variable, x minus 3 e to the power of 2x plus 8. This is our initial value problem, initial value solution. And I do have a graph, so we don't need the graphs. That's, please don't, don't worry, we can see we have this solution. And before having an initial value problem, all of the blue lines represent this function. If we will use, for instance, Desmos, we can get these graphs. We will shift up and down, but we wanted this one particular one. This point is 0, 5, which that was the condition. Okay, at x0, the value is 5. We did substitute, we computed constant c, we get 8. And yes, that's the particular, the pink one is our function. This function behaves, but we can see the other families of the functions with respect to the rate of change, they behave the same. Like, for instance, slope of the tangent for the particular x, of course, I pick the horizontal, is the same. And slope of these curves will be the same for the particular x value. Okay, example number 2. Solve differential equation dy dx equals to x squared over y squared. Find the solution of this equation that satisfies the initial condition y at 0 equals to 2. If x is 0, the value y is 2. Okay, perfect. Let's solve it. This is nice separable differential equation. Okay, we will split. I will multiply both sides by y squared, and I will move the x on the other side, multiply by dx. Now it's the moment of integration. Integral of y squared dy is y cubed over 3, and the same for x squared, x cubed over 3. And you may notice I still add the constant, but as we know, I will combine this and I will name this as a new constant. Okay, that's the new constant. And now we have to still solve for y because we're looking for the formula for the unknown function. Multiplying by 3, okay, both of the side. Again, you can see we have 3 times constant, but this will be again constant. Doesn't matter if it's 3 times constant, 4 times constant, it's just the constant, another constant. Taking cube root of both sides, we're finalizing the equation and we have this constant. Okay, cube root of x cubed plus c. This is part A. And we also have part B. Let's substitute 0 instead of x. And the whole equation is 2. Of course, cube root of c equals to 2. Cube root of 8 will give us 2. c is 8. Cube root of x cubed plus 8. And I hope we're not thinking to simplify this form. Yes? Both of the numbers, x cubed plus 8, actually plus 8, they are involved in addition. We are not allowed to just take the cube root. That's the final form. And I do have the graph. Again, if we will have, this is function cube root of x cubed plus the constant, all of the blue. But if this is 8, that's our, actually that's 8, right? Oh, no, that wasn't 8. That was actually y at 0 was 2. That's 2. Okay, that's 2. Okay, another one. Solve this equation. dy dx is equal to 6x squared over 2y plus cosine y. Let's make the separation. Multiplying by 2y plus cosine y, keeping dy, keep 6x squared and move dx on this side. We can integrate. Integral of 2y dy is y squared. Integral of cosine y dy is just sine y. And I will add the one constant on the right-hand side. Integral of 6x squared is basically 3x cubed. No, 2x cubed. 2x cubed. Okay, and we have a constant. However, what we may notice that this function is not actually easy to solve to isolate y on the left-hand side. Because we have quadratic function, y squared, trigonometric, sine of y, it will be not easy. In this case, we will basically use this implicit, we will use simply this implicit way of presenting the solution, because this equation, the final box equation, doesn't include derivative. It's not a differential equation anymore. Just representing function y in the implicit way. And I do have this equation here, and all of the, we didn't really have the initial value, initial condition, then all of these colorful curves represents this equation, respectively with the constant being 3, 2, 1, 0, -1, -2, -3. Okay, we have another one. Okay, solve the equation. Y prime equals to x squared equals to y. I will say dy dx, because x is independent, equals x squared times y. I will divide by y both sides, and I will move dx. We are ready to integrate. Integral of 1 over y dy is natural log of y. And I will add the constant at the end. X squared is x cubed over 3 plus that common constant. Now we will use the exponential. We know that e to the power of this number is y, right? The exponential form. I will move this. Okay, actually y is e to the power of x cubed over 3 plus the constant. But let's change this equation a little bit, this solution. Adding the exponents means that we can multiply the same base, the same e. We have a multiplication. That addition indicates this multiplication. And again, we remember e to the c is basically a constant. Okay, that's when we have this equation as a e to the power of x cubed over 3 times the constant c. That's the way. And now, quantity y could be the inside quantity, could be positive or negative, because we will take the absolute value at some point. That we can, because c could be positive or negative, we can say this is the solution. It's just exponential function, exponential model, e to the x cubed over 3 and some constant. Okay, and I think I have the graph. Oh, I have the solution. Excellent. Okay, we can see I just use different a, but it's just a constant. Oh, okay, so this is, we can actually say c, because I was trying to. This represents the solution, is the exponential function. C doesn't look like c. I just want c. Again, I use Desmos c times e to the x cubed over 3. Depends what c is. We may have different curve. But this one, I just wanted to show you. These little line segments, this is called the slope field. Because before having this solution, like we good, because this one was easy, we solved it. We just have the rate of change was defined as a x squared times y. It was the equation, yes, x squared times y. Now what we can say, without having the solution, that right-hand side is defined as a derivative. This is basically slope of y. And if I will get x value and y value, simply coordinates, for instance, 1, 1. 1, oh, it's a little bit weird, but yeah, let's see here. Then the slope is 1. Yeah, the slope is 1. For instance, if x is 0, then doesn't really matter what is y, the slope will be always 0, 0, 0, horizontal. If y is 0, also the slope is 0. That's what we can see. If, what else we can figure out? Can we figure out something? If, yeah, actually it's, okay, that's actually some of the, because of course, then we can say like 4, 2, for instance, 4, 2. That slope will be quite steep because x is 2, 2 squared is 4, and y is 4, 16. The slope will be 16. And doing this by hand, of course, is crazy, but when we ask computer, we can get thousands or millions of this tiny line segment, which represents the slope, and we may see the function. We can probably see through like some of the functions that will satisfy this solution, this differential equation. Okay, but of course we will, as I just want to tell you, but this is in section 9.3, and we will not cover this section. Okay, let's look the next equation, because as you can see nicely, we're focusing on separable differential equations. dy dx equals to 6xy squared, and we have to find particular solution. Okay, what we will do, I will divide both sides by y squared, keep dy, keep 6x, and multiply by dx. Separation is done, let's integrate. Integral of 1 over y squared dy is, I can write here, it's y to the negative 2, and it will be y to the negative 1 over negative 1 over y. Negative 1, yeah, just in case, if we forget. And I can remove this. Yeah, you can definitely. And integral of 6x dx is 3x squared plus the constant. Okay, now what I will do, first of all, I will multiply by negative 3x squared, and negative c will become just a constant, just a new constant. And now I will flip function 1 over negative 3x squared plus the constant. Okay, but also I would like to show you, just in case if you will decide that first of all, you actually flipping a number. Okay, that means when you flip the number, we will end up with negative y 1 over 3x squared plus the constant. And now we're multiplying everything by negative. We can write like this, and it's still the same thing. Or, of course, you can put that negative in front. Doesn't matter. But now, when you will decide to distribute this negative in the denominator, we will have negative 3x squared and negative c, but negative constant is just the constant. It will be actually that function. Okay? But what I am saying, I'm trying to show you just all of the box equations are the same equations. Yeah, you can watch them, you can maybe look again arithmetically, and just for the purpose of multiple choice that we have to remember that we may, how we playing with this constant. Also, you may notice I'm keeping this constant in the denominator. It's not like outside the denominator. No. Okay, now we can try to find one particular solution. Let's compute the constancy. I can use this equation. If x is 0, y is negative 1. 1 negative 3 times 0 equals to negative 1. 1 over c equals to negative 1. C basically is negative 1. Okay, c is negative 1. And function will be, I can maybe write, actually I can write here, because that was the same function. Function, the final answer will be 1 negative 3x squared minus 1. Okay. Probably when we will use this equation, or this, because they are the same, we will get constant c equals to 1. But now when we have the particular constant 1 and applying that negative will become negative 1. That means everything is good. Okay, this is our function. Oh, the solution for the equation. And you can even see, like you can check this solution. I think it's this way, but when I apply this negative denominator, then I am having negative 1, because now I have one particular value. Okay, and our function is the pink one. The rest of them is just the family of the functions with the constants. The pink one is our initial value problem. Okay, let's solve another one. Find the explicit solution to the initial value problem y prime. Y prime equals to e to the power of t minus y. And then initial value is, if t is 0, the value of the function is natural log of 3. Okay. dy dt, this is derivative with respect to t, and e to the t times e to the negative y. And we're trying to make the separation dy dt, e to the t. Oh, no, because negative e to the t, e to the y, because I can place this in the denominator. We may kind of cross multiply e to the y dy, e to the t dt, and we are ready to integrate. E to the y, integral of e to the y dy is just e to the y. Integral of e to the t dt is just e to the t and plus the constant. Okay. Now we have to solve for y. I will take natural log of both sides, ln and ln. Left-hand side and the entire right-hand side. Now we can see we're keeping that constant because that's different. Now we know that that y can travel in front as soon as we have logarithmic. We can keep this. And ln of e is basically 1. Y equals to natural log of e to the t plus the constant c. And we will keep the function like it is. Okay, so this is general solution. Y at 0 equals to natural log of 3. Natural log e to the power of 0 plus the constant equals to ln of 3. Natural log 1 plus the constant. And since natural logarithmic function is continuous function and it's increasing, we can drop this and we can say 1 plus constant equal to 3. Constant is basically 2. Now we can finalize and we can say the final equation with respect to t is natural log e to the power of t plus 2. This is the solution of this differential equation, initial value problem. Okay, I have just one more thing and we will be done. Okay, also, we have nice simple equation which looks like this. dy dt equals to k times y. This basically indicates that the rate of change of y, which is dy dt with respect to time, the rate of change of y, it's proportional to the function itself. Dy dt equals to just k, some coefficient, times the function y. Okay? And this basically, this equation, it's actually used to model a couple of things. And for instance, I have a couple just of examples, some growth of population, spread of the computer virus, and maybe not only the computer virus, some growth of decay of the radioactive substance, elimination of the drugs from the patient bloodstream. I mean, it's the model of growing, and actually it's the model of growing or decaying, increasing or decreasing the amount, the initial amount. The proportionality of constant k in these differential equations is negative. If k is negative, we will have elimination, we will have decay. If k is positive, we will have some growth, some spread, which of course will indicate that y is increasing and y is decreasing in the other situation. Okay? But we can see, basically we can also say y prime equals to k times y. And you remember one of the equations I asked you at the beginning, most likely the solution will involve exponential function. We will try to solve it. In a minute, we will try to solve this equation. Okay. because we even know the growth and decay, it's always the exponential growth, exponential decay. Let's actually see, let's uncover now this phenomena. Okay, dy dt equals to ky. So dy dt, the rate of change of the function y, it's proportional to the function y itself. I will divide by y both sides, and I will multiply by dt, or I can say I will move dt. Okay, integral of 1 over y dy is natural log of y. Integral of k dt is just kt plus the constant. And now y equals to e to the power of kt plus the constant. We will use the property like we used before, e to the power of c. Of course, the constant is another constant. Then y is e to the power of kt times that constant. And since constant could be positive, negative, we will just, in general, we will have this equation. Okay, that means this is the solution, c e to the power of kt. It's definitely the exponential. And let's assume at the moment that constant c is positive, because we theoretically need positive. This is y, this is t. And if k is positive, we will have exponential growth. Right? This is actually the initial value c. That's the initial value, because if time is 0, e to the power of 0 is 1. The initial value will be constant c. But now if, and this is when k is positive, if k is negative, then we have decay. Okay, both of them supposed to intersect here. Okay, we did solve this model. And what we can do, we do have some, of course, we know exponential growth, exponential decay. Let's just solve one question which involves this model, and we will be done with section 9.1. Okay, example number 8. Escherichia coli bacteria grows such that the rate of change of the population is proportional to the population present. Okay, we can see important, the rate of change of the population is proportional to the population present. From that sentence, from that wording, we can say this: the rate of change of the population, let's say p prime, or if we like derivative of p with respect to time, it's proportional to the function itself, to the population present. We don't know k. Let's say just p. Okay. We don't know the constant of proportionality. Assume that 1,000 bacteria are initially present. Good information. If time is 0, number of bacteria is 1,000. And if time is 1 hour, after 1 hour, 1,500 are present after 1 hour. 1,500. This will give us some information as soon as we have the function p, because we only have the model, we only have the differential equation. We can solve this equation for p and then solve the system of two equations to compute the constant of proportionality k. Okay, determine p of t, the population after t hours. Okay, that means this will be, let's say, part A. Okay, let's solve it. We just did it, but let's solve again. Okay, let's try on my pen. Okay, I will divide by p, keep dp, I will keep the constant k and dt. Now is separation done, the moment of integration. Integral of 1 over p is ln of p. Integral of k dt is kt plus the constant. And then p is e to the power of kt plus c. And then we know that that c will become a coefficient. And actually, basically, this is the solution. P function p equals to c times e to the power of kt. We knew it. But now, that means this is that's still not completely the formula, because we need the coefficient. We need the coefficient k. What I will do here, p at 0, that means c e to the power of k times 0 equals to 1000. And then c e to the power of k times 1 equals to 1500. Okay, e to the power of 0, of course, is 1, c equals to 1000. Because always when time is 0, that's the initial amount. That's the initial amount. Okay, now I can substitute 1000 e to the power of k times 1, and we have to solve it for k. Dividing by 1000, it will be 1.5. Am I right? Okay, and then k is natural log of 1.5. Yes, I took the log ln of both sides. We probably okay with this process, and normally we will leave it. But if it's like a question like during the class, or if it's the homework assignment, we can use the calculator. And I did. Logarithmic function of 1.5 is 0.405. Okay, this is our constant of proportionality. I can write a function p of t equals to the constant, which is initial, e to the power of point, am I right? 405t. This is function. Yeah, I just copy this function with the information c and constant of proportionality. Okay, we have our function. That's our function. Okay, let's actually finish what we have to finish. How large is the population after 5 hours? Okay, basically after 5 hours, this will be part B. Part B, we have to just substitute 5 instead of t. 1000 e to the power of 0.405 times 5. And I believe I use the calculator. Oh, let me check. Is 7,576. Of course, that's the amount of, that's how large is the population, amount of bacteria. Okay. Oh, a little bit crowded, but I'm trying to organize the solution. Okay, and we have part C, the last one, of course, we will not miss any. How long does it take for the population to double in size? We don't see the word double. How long does it take the population to double? Okay, that means if the initial amount is 1000, then the expected value is supposed to be 2000, double. Yeah, as simple as it is. If the initial amount is 1000 of this model point, and we need 2000, we just have to solve this equation for t. When we divide by 1000, we will have this, and when we will take natural log, we will have 0.405t, because natural log of e is 1, and then basically t is that number divided by natural log of 2. and I use the calculator, I got 1.71, and this is time. Time is in hours. A little, almost 1 1/4. 1 hour and 0.71. We can exactly, if this will be 75, it will be 45 minutes. But yes, 1 hour, 1.71 in decimals hours. Okay, that's in all. Basically, I would say part A, it's the calculus, it's the differential equations. With the equation, we did it, but we also decipher all of the words, have the equation, get the numbers. And yes, we did solve the question, the application. Okay, this is everything for separable differential equations. Please check the other section for the other video for the section 9.2. Thank you.